Section 6.3, Logarithms and Logarithmic Functions. We're going to start off with a couple of basic examples, and it kind of leads me to why we're talking about Section 6.3. So, number one, 2 to the x power equals 4. What we're basically figuring out is 2 to the what power is 4. Well, that one clearly is 2, because 2 squared is 4. Same thing with number 2. 3 to what power is 27? Well, I'm pretty sure that 3 cubed is 27, so then x is equal to 3. Well, now we need to figure out number 3. 2 to what power is 10? Well, we know that 2 to the third power is 8. 2 to the fourth power is 16. That doesn't really help us get to 10, though. We need to find a value for x that makes it, or that allows us to raise 2 to that power to get 10. And that is kind of, that's what leads me to this next slide here. Logarithm of y with base b. Okay, here's how this is written. So we got log base b of y is equal to x. Okay, so how we say this, log base b of x. Okay, log base b, not of x, silly me. That is log base b of y, and that is equal to x. Okay, this is logarithmic form. Logarithmic form. Well, why is that important? Well, there's another way we can write this, where we could have b to the x power is equal to y. Okay, this one here is exponential form. Exponential form. These two statements right here, okay, are equal. You could put the log base b of y is equal to x if and only if b to the x is equal to y. Notice that we have the same variables here, and they represent the same things. Okay, those two expressions there, the one in black and the one in red, they are equivalent. Okay, one is logarithmic form, one is exponential form. They are exactly the same. What I want you to notice, or what I hope you notice, is that when we use logarithmic form, what we're actually solving for is x, and x in the red one is the exponent. So we would use logarithms to solve this third example here on the first slide. How would we get x by itself? Well, we would need to take a logarithm to get the exponent by itself. Okay, so let's do some examples. We're not going to actually do any solving right now. We're just going to get comfortable writing logarithms and understanding how the two are similar, whether it's logarithmic form or exponential form. Okay, so the directions: rewrite each equation in logarithmic or exponential form. We're going to start with logarithms and turn them into exponents, and then we'll do the exponents and turn them into logarithms. Okay, so number 1, we got the log base 2 of 16 is equal to 4. Okay, remember we have log base b of y is equal to x, and then that turned into b to the x power is equal to y. Okay, so your base is here, so your base in your exponential form is going to be 2. Your exponent is this one right here, so 2 to the 4th power, and then it's equal to what you were taking the log base 2 of, so 2 to the 4th is equal to 16. Let's try another one here. So number 2, we've got the log base 4 of 1 is equal to 0. Okay, so start with your base, the bottom number, 4. The number on the end of your equation is your exponent, 4 to the 0, and then that's equal to what you were taking the log base 4 of. 4 to the 0 equals 1. That should make sense. Any number to the 0 power is 1, but we're using 4 in this case, so 4 to the 0 is equal to 1. Number 3, let's try another one here. The log base 12 of 12 is equal to 1. Okay, again, start with your base, which is 12. Then your exponent on the end is 1, and then that is equal to your third number, 12. 12 to the first power is equal to 12. Let's try one more in here. The log base 1/4 of 4 is equal to -1. One more time. Start with your base, 1/4. Start and then go to your exponent right here, -1, and then that is equal to the last number, 4. 4 to the -1st is equal to 4. That was that's the bell here at school that just went off. Remember what I said in the video for exponent properties? Anytime we have the negative first power, that essentially means reciprocal. So the reciprocal of 1/4, because this says 1/4 reciprocal, well, that's 4. Flip the fraction over and that gets you 4. So that should make sense. Let's try going the other direction. Okay, so number 5. Now I'm going to give you something in exponential form, like 5 to the second power is equal to 25. And let's see if we can't turn this into logarithmic form. Okay, so I'll leave these two examples here so we can see them, and then we can go from there. Okay, so we start with the word log, and then what you notice here in this one, the bottom number is your base of the exponent. So the base of the exponent here is 5, so log base 5. Now if we go back to the logarithmic form, what it was, so we had log base 4 of something. That number was actually what it was equal to. So this should be underlined in blue. Log base 5 of 25 is equal to, and then the last thing was your exponent. 0's on the end, 0 is your exponent, so then your exponent here is 2. So log base 5 of 25 is equal to 2. Let's try another one here, number 6. 10 to the negative first power is equal to 1/10. Okay, so start with your base. So we got the log base 10 of your answer, original answer, 1/10. Whoops, that should be in blue, sorry. 2, that's in blue. 1/10 is equal to your exponent of -1. Log base 10 of 1/10 is equal to -1. Let's try a couple more here. Number 7. If at any time you want to try these on your own, feel free to pause the video and then I'll just go through it when you're ready. 8 to the 2/3 is equal to 4. Again, start with your base. Log base 8 of your exponent, or sorry, of your answer, 4, is equal to your exponent 2/3. So log base 8 of 4 is equal to 2/3. Whoops, that's not number 2. This should be number 8. Let's try one more here. 6 to the negative third power is equal to 1 over 216. Again, start with your base. So we got the log base 6 of your answer, 1 over 216, and that is equal to your exponent of -3. Hopefully you're starting to make the connection between exponential and logarithmic form. They do mean the exact same thing. They are equivalent statements. I want to talk about two special or certain kinds of logarithms. The first one is the logarithm of the number 1. Logarithm of 1. So if we have the log base b of 1, okay, every time you take the log base whatever of 1, the answer is always 0. Because if we turn this into exponential form, it would be b to the, this is your exponent, 0 is your exponent, okay, so this would be b to the 0 power, and any number to the 0 power is always going to be 1. So if you're ever taking the logarithm of 1, your answer is always going to be 0. The other special logarithm I want to talk about is the logarithm base b of b. Okay, we saw an example with that. That would be this one right here, example number 3, log base 12 of 12. So these two numbers are going to be the same. That's what this special property is discussing. Okay, so we got the log, whoops, need the pen back, log base b of b. Anytime you have b, log base b of b, your answer is going to be 1. Okay, because remember this number here is your exponent, your base. This is your exponent, b to the first power. Anytime you have anything to the first power, your answer is always going to be itself. Okay, so the logarithm of base b of b. So if your base and what you're taking the logarithm of are the same, your answer is going to be 1. If you're taking the logarithm of 1, answer is always going to be 0. And that's what those two special logarithms discuss. Okay, so let's move on to actually evaluating logarithms. Let's try figuring out what some logarithms are equal to. Okay, so let's start off with this one, log base 4 of 64. Okay, so how we're going to think about this is we're going to think about it this way. This number, the bottom number, your base, we're going to think 4 to the what power, 4 to the what power is 64. Okay, That's really the question that you're being asked here with this example. Log base 4 of 64. 4 to the what power is 64? If you have your half sheet handy, what you're going to find that 4 to the third power is equal to 64. So your answer here for number 1 is not 4, it is 3. So your answer, the log base 4 of 64, is equal to 3. Number 2, let's try another one here. We got the log base 5 of 0.2. Okay, we're going to figure out what that is equal to. Okay, so let's think about doing this in exponential form. Your base is 5. We don't know the exponent, but we know that when it's raised to that exponent, our answer is 0.2. But 0.2, if we turn that to a fraction, is 1/5. 2/10 simplifies down into 1/5. Okay, 5 and 1/5, well, those are reciprocals of each other. Okay, to get something to be a reciprocal, your exponent has to be -1. The negative first power means reciprocal. So our answer here for number 2 is -1. I'm going to erase some of this just so I have a little more room to write. Okay, slide that up. Number 3. Let's try the log base 1/5 of 125. Okay, again, turn it in, think about it exponential form. The base 1/5, we're going to raise it to what power to get 125? Well, if it was 5 to the some power, that answer is easy. That's 3. But it's not 5, it's 1/5. It's the reciprocal of 5. So let's think about it as 5. If we thought about this as 5 to what power is 125? Well, that answer is easy. That one's 3. Okay? But we need the reciprocal. And anytime we have reciprocals involved, that means our exponents have to be negative. So our answer here for number 3 is -3. Okay? Because the reciprocal cubed of 1/5, reciprocal is 5, cubed gives you 125. So -3 is your answer for number 3. And then the last one here, number 4, log base 64 of 8. Again, think about it exponentially. Slide this up here. 64 to what power is equal to 8? Well, the question, I know 64 and 8. 8 is the square root of 64. So if I did the square root of 64, that would be 8. To turn a square root into an exponent, remember the square root is the 1/2 power. Okay, so 64 to the 1/2 power is 8. So your answer here for number 4 is going to be 1/2, because it's 64 to the 1/2 power, or the square root of 64. Okay, so there's a little intro on evaluating. We're going to do some more practice with this, so if you're not getting it, maybe jot down some questions, ask me the next time you see me. But I'm not expecting you to have this mastered as you're watching this, okay? Another school bell going off. Let's keep moving. Special logarithms. These are the logarithms that your calculators can do. We'll underline those in blue. Sure, why not? Okay? 2 vocabulary terms, common logarithm and natural logarithm. Common logarithm is a logarithm with base 10. In your calculator, you're looking for the button that says LOG, log. Anytime you see a logarithm written without a base, like these two right here, that I've got examples that we'll get to in just a second. If you ever see something written without a base, a logarithm written without a base, we assume that it is base 10. Okay? If it's not base 10, there will be something written there for the base. So, logarithm is, or a common log is the log with base 10. It's the log button on your calculator. It's right next to the 7 if you're looking at your graphing calculator. The natural logarithm, if you remember from 6.2, we talked about the natural base, which is the number e. So it makes sense that the natural logarithm should be the logarithm with base e, or the natural base. Your calculator also does natural logarithms. It's the ln button. I guess on the calculator, looking at it, it's capital letters, but it's ln. Okay, that's how they shorthand natural logarithm, or logarithm with base e, is ln. Okay, and I've got a couple examples down here also of using natural logs. Okay, so let's try these. Evaluate using a calculator. I'm not saying that you got to know what certain logarithms are equal to. Some of them are maybe a little simpler than others, but for these 4 examples that I've got here, log of 8, log of 12, natural log of 0.75, natural log of 5, I'm not expecting you to know what these are ever. Okay, so that's why we say evaluate using a calculator round to 3 decimal places. So, for the calculator, just hit the log button, type in the number 8, and hit enter, and then you'll have your answer for number 1. When you do that, this should be approximately 0.903. And what this answer really means is that if we have a regular log, the base is 10, This is our exponent, remember, our answer. This is our exponent, so 10 to the 0.903 power. If we were to type that in, we should get something very close to 8. So that's how you can kind of check yourself to make sure you're doing things right. Log of 12, not log base 12, log of 12. Again, just type it in your calculator. That one should be 1.079. Natural log, again, we're just using a different button, but it's the same idea. Natural log of 0.75 should be negative 0.288. Negative 0.288. And then the natural log of 5 is about 1.609. Again, with these two, that's like e to the 1.609 should be approximately 5. That's how you can kind of check yourself using the proper base. All right, the last thing in the section, graphing logarithmic functions. It's a little different than every function we've graphed so far. Every function in Algebra 2, whether it's linear, absolute value, quadratic, cubic, fourth power, fifth power, whatever, polynomials, radicals, anything like that, we've always chosen x values and then we find the y's. With logarithmic functions, though, it's opposite. We're going to choose the y values instead of our x values, and I'll show you why. Okay, because if we have y equals the log base b of x, because that's what your functions are going to look like. If we wanted to turn this into exponential form, something that we might know more how to do in our heads, remember your base is b, this becomes your exponent. B to the y is equal to x. So when we choose our y's, all we're taking is our base to that exponent and then finding our x values. Okay, so that's the reason we choose y values instead of x, is because it's easier when we turn it into exponential form to graph and to come up with good ordered pairs. Okay, so let's try an example or two. Number 1, f of x is equal to the log base 3 of x. First thing we should do, forget the f of x, let's make it y. Y equals the log base 3 of x. What we're going to do next is turn it into exponential form. Remember, there's your base, 3. This becomes your exponent. 3 to the y is equal to what you were taking the log of. So 3 to the y is equal to x. So what we're going to do now, we're going to make our table, xy table. 1, 2, 3, 4 spaces, or 4 lines gives you 5 spaces. And we're going to choose our y values this time. I'm going to go with the standard 5, negative 2, negative 1, 0, 1, and 2. And then to find the x values, just plug these numbers right here into that variable. 3 to the whatever power is going to give you x. Okay, so let's start with the 0 power here. Okay, so 3 to the 0 power, any number to the 0 power is 1. 3 to the first power is 3. 3 to the second power is 9. 3 to the negative first power. Negative first power means reciprocal, and the reciprocal of 3 is 1/3. The negative second power means reciprocal squared. So the reciprocal of 3 is 1/3. Squared, 1/3 times 1/3 would be 1/9. Now, let me bring in some graph paper here. When we graph, and I'll come back, we'll go back and forth between these x's and y's. Let me draw my graph here. So 1, 2, 3, 4, 5, 6, 7, 8. I don't think I'm going to quite get to 9, be right on the edge, but that's okay. And then my y value is 1, 2, 1, 2. Okay. When we graph, we still graph in the ordered pair form, x comma y. So this point right here, 1, 0, okay, when we graph, 1, 0 is right here. Okay, we're not on the y-axis, we're actually on the x-axis this time. Okay, the rest of them, 3, 1, so 3, 1 is there. 9, 2, 9, 2 would be right about in there, be right on the edge of the screen, so I'll mark it right there. It's not quite exact, but close enough. 1/3, negative 1, so negative 1 is my y value, 1/3 is my x. That's less than a half, so maybe about in there. And then 1/9, negative 2 is really close to the y-axis, but not quite on it. Okay, so our graph, our function, looks something like this. Okay, it's got the same shape as an exponential function, but not the same orientation. What you're actually going to find, and what we could talk about later, not in this video, but in class, is that logarithmic functions and exponential functions are actually inverses of each other. So if we wanted to, we could draw this nice y equals x line and do an exponential growth function, and it would look something like this, and then you have that nice reflection. But that's beyond the point, not really what we're talking about today. So let me get rid of all those dashes. 1, 2, 3. Okay, they're all gone. Okay, so there's the graph of y equals, or f of x equals the log base 3 of x. What you should notice is that you have an asymptote here. Asymptote in your graph. If you keep going farther left this way with your y values, what you're going to find is your x values get very, very small, but they're never going to get to 0. Okay, so your asymptote here in this picture is the y-axis. You're never going to find an x value of 0. Okay, because you couldn't raise b to any power to get 0. B to something is never going to be 0. Okay, you could pick a very small, but you're still dividing by 3 essentially. You're never going to run out. And then obviously, as we get larger with the y values, our x values get very big too. Okay, so let's try one more here. I'm actually going to change the page, bring in the graph paper again. So number 2, we're going to have g of x is equal to the log base 1/2 of x. Okay, so first thing, again, switch g of x out for y. So we'll have the log base 1/2 of x is equal to y. And then we'll go ahead and turn that into exponential form. So that would be 1/2 is your base, 1/2 to the y power is equal to x. And then we'll choose some x's and y's. x, y, 1, 2, 3, 4. Again, we're choosing y values, so -2, -1, 0, 1, and 2. Again, to find the x values, plug in the y's, just like always, but we're just using our variables in reverse. Okay, so if we plug in 0, 1/2 to the 0 power, any number to the 0 power is going to be 1. 1/2 to the first power is 1/2. Any number to the first power is itself. 1/2 squared, 1/2 times 1/2 is 1/4. 1/2 to the negative first power, the negative first power is the reciprocal, so the reciprocal of 1/2 is 2. Reciprocal squared, so for 1/2 to the negative second power, square 2, that gives you 4. And then we can go ahead and sketch our picture. So I'll bring in my XY plane here, something like that, and we can go ahead and plot our points. I guess I can mark 1, 2, 3, 4, 1, 2, 1, 2, whoops, 2, 1, 2. Not a great XY plane, but it works. It'll work for what we need it to. So let's just go ahead and plot these points. 4, -2 is way down here. 2, -1 is right here. 1, 0 is here on the x-axis. 1/2, 1 is right there. And 1/4, 2 is going to be right there. So then we have our picture. Again, never going to get to the y-axis. We have another asymptote at the y-axis. Asymptote at the y-axis. Okay, we're never going to have an x value of 0. We'll never find one. Okay, so a couple of examples there of graphing logarithmic functions. Hopefully that makes sense. If you have questions, please write them down. Please ask me the next time you see me.